Good afternoon to everybody. In last lecture, we have studied different blocks of file system: boot block, super block, inode block, and a data inode list, and a data block. Then we move towards a processes. A process it describes the structure of process, and some process data structures used in memory management. Then it gives a primary or basic view of process state diagram, and there are various issues involved in some transitions. A process is the execution of program, and it consists of a pattern of bytes that a CPU interpret as a machine instructions called as text, then data and stack. So whenever there is execution of a process in a program execution, it consists of a pattern of bytes such as some machine instructions known as text, data, and a stack. So many processes appear to execute simultaneously as kernel schedules them for execution. Several processes may be instance of one program. So one program have several processes. So a process execute by following a strict sequence of instructions that is self-contained and does not jump to that of another process, that it read and writes its own data and stack section, but it does not or cannot read and write the data and stack of other processes. Processes communicate with other processes and with the rest of the world through a system calls. So in practical terms, a process on Unix system is the entity that is created by fork system call, and every process except process 0 is created when another process executes the fork system call. The process that invoked the fork system call is the parent process. The process that invoked the fork system call is known as parent process, and the newly created process is the child process. And every process has one parent process, but a process can have many child processes. So the kernel identifies each process by its process number, that is a process ID or PID. And process 0 is a special process created by hand when the system boots or after orbiting a child process, that is process 1. Process 0 becomes a swapper process. So process 1 is known as init. It is the ancestor of every other process in the system and enjoys a special relationship with them. So a user compiles the source code of a program to create an executable file, and it consists of two parts. First, a set of headers that describes the attribute of file, and second, the program text, a machine language representation of data that has initial values. A machine language, a representation of data that has initial values. When the program starts execution, a machine language representation of data has initial values. When program starts execution, and an indication of how much space the kernel should allocate for uninitialized data called as BSS2. The kernel initializes it to a 0 at the runtime. So kernel loads the executable file into memory during execution system call exec, that is execution system call, and loads. The process consists of the at least three parts, that is text, data, and stack. The stack consists of logical stack frames that are pushed when calling function and popped when returning. A special register is called as a stack pointer, and which indicates the current stack depth. So from the stack frame, which contains parameters to a function, its local variables, and a data necessary to recover previous stack frame, including the value of program counter and stack pointer at the time of function call. The program code contains instructions sequences that manage stack growth, and kernel allocates a space for the stack as needed. The kernel stack contains stack frames for functions executing in kernel mode. The function and data entries The function and data entries on the kernel stack refer to functions and data in the kernel. The function and data entries on the kernel stack refer to functions and data in the kernel, not the user program, but its construction is the same that of the user stack. So the data entries and function on the kernel stack used in kernel, not the user program. So kernel stack of process is null when the process execution in user mode. So every process has an entry in kernel process table, and each process is allocated a user area that contains private data manipulated only by the kernel. The process table contains or points to a per process region table, and whose entries point to entries in a region table. And a region is a continuous area of processes address space such as text, data, and stack. Region table entries describes the attributes of region. Region table entries describes the attributes of region such as whether it contains text or data, whether it is shared or private, or where the data of region is located in memory. The extra level of indirection from the per process region table to the region table, which allows the independent process to share region. When a process invokes the execution system call. The kernel allocates a region for its text, data, and stack. After freeing the old regions the process had been using. So this is the figure for process table. It contains of different three different tables. So process table which have allocated as user area. U area is the user area. Then after process table there is per process a region table. Then there is a region table and then connected to main memory. This figure shows the relevant data structure of running process. The process table points to per process region table with pointers to the region table entries for the text, data, and stack region of the process. The process table entry that user area contains the control and status information about the process. The user area is an extension of process table entry. So fields in the table are discussed as the state field, then identifiers containing the user who owns the process, that is UID or user's ID, and then an event descriptor set an event descriptor set when a process is suspended in sleep state, and the U area contains information describing the process that needs to be accessible only when the process is executing. So user area contains information describing a process that needs to be accessible only when the process is executing, and the important fields are a pointer to the process table, slot of currently executing process, parameters of current system call, return values and error codes, then file descriptors for all open files, internal input output parameters, current directory and current root, process and file size limits. So the kernel can directly access the fields of the user area for executing process, but not of the user area of the other processes. Internally, the kernel references the structure variable user to access the user area of currently running process. When another process executes, the kernel rearranges its virtual address space so that use, structure user refers to the user area of new process. The implementation gives the kernel an easy way to identify the current process by following pointers from the user area to its process table entry. So first is context of process states, then state transitions, sleep and wake up. So what is the context of a process? The context of a process is a state as defined by its text. The values of its global user variables and data structures. the values of machine registers it's uh, it uses, the value stored in its process table slot and user area, and then contents of its user and kernel stacks. The text of operating system and its global data structures are shared by all processes but do, do not constitute the part of the context of process. When the executing process, the system is said to be executing in the context of the process. When the kernel decides that it should execute another process, it does a context switch so that the system executes in the context of the other process. The kernel allows a context switch only under specific conditions. We will see, we will see uh, when doing the context switch, kernel saves the enough information so that it can later switch back to the first process and resume its execution. When moving from user to kernel mode, the kernel saves enough information so that it can later return to the user mode and continue execution from where it left off. Moving between user and kernel mode is a change mode, not a context switch. Kernel serves interrupts in the context of interrupted process, even though it may not have caused the interrupt, and the interrupted process may have been executing in user mode or in kernel mode. The kernel saves enough information so that it can later resume execution of the interrupted process and services the interrupt in kernel mode. The kernel does not spawn or schedule a special process to handle interrupts. Then process states. The lifetime of a process can be divided into set of states in which a certain characteristics describes the process, which are essential to understand the following states now. So there are four states. First, the process is currently executing in user mode. Second, the process is currently executing in kernel mode. Third, the process is not executing, but it is ready to run as soon as the scheduler selects it. Many processes may be in this state, and the scheduling algorithm determines which one will execute next. It depends on the algorithms such as first come first serve, shortage of first, and shortest remaining time next. Then step 4, the process is sleeping. A process puts itself to sleep when it can no longer continue executing, such as when it is in waiting for input output to complete, because a processor can execute only one process at a time. A processor can execute only one process at a time, At most, one process may be in state 1 or state 2 or in both. So the two states corresponding to the two modes of executions, user mode and kernel mode. Then next part is state transitions. The processes move continuously between states according to the well-defined rules. So the process state transition diagram is a directed graph whose nodes represents a state of the process can enter and whose edges represents events that cause a process to move from one state to another state. And the state transitions are legal between two states if there exists an edge from first state to second state. Several transitions may emanate from a state, but a process will follow one and only one transition depending on the system event that occurs. So this is process a state a transition diagram. See figure carefully.
Sir,
Hello. So there are four states. First state is user running state. Second state is kernel running state. A third state is ready to run, and fourth state is asleep. So if the process is ready to execute from user mode to the kernel mode, so system call or interrupt that process and process enters from first user state to kernel state. If that process requires or process is no longer running or no it requires more time, it goes to the sleep. Then the whenever context switch permissible, the system process will wake up. Then it goes to the state ready to run, and as per scheduling algorithm, the kernel schedules the process for the execution through kernel mode. When there is interrupt, then interrupt and remove that interruption. Okay. When there is a no process in kernel mode for execution, then it will execute that process through kernel. But if there are number of processes, and so some of number of processes in queue for execution, so some of process gives goes to the sleep mode because they does not execute or execution does not start for no longer time. Then when after that context a switch permissible, then that processes wake up and go to the ready to run state so that process executes. So in this state, a ready to run state, there is there are number of processes. So which process will be going will be execute. So the processes are execute will be executing the processes will be execute as per the scheduling algorithms, first come first serve, shortage of first, or shortage remaining time next, and go to the kernel running state. So several processes can execute simultaneously in time sharing manner. As stated earlier, they may run simultaneously in kernel mode. If they were allowed to run in kernel mode without constraint, they could corrupt global kernel data structures by prohibiting arbitrary context switches and controlling the occurrence of interrupts. The kernel protects its consistency. The kernel allows a context switch only when a process moves from a state kernel running to process state asleep in memory. From this state 2 to state 4, processes running in kernel mode cannot be preempted by other processes. Therefore, kernel is sometimes said to be non-preemptive, although the system does preemptive processes that are in user mode. The kernel maintains consistency of its data structures because it is non-preemptive, and thereby solving the mutual execution exclusion problem, making sure that the critical sections of code are executed by at most one process at a time. So to review, the kernel protects its consistency by allowing a context a switch only when a process put itself to sleep and by preventing one process from changing the state of another process. It is it also raises the processor execution level around critical regions of code to prevent interrupts that could otherwise it causes the inconsistencies. The process scheduler periodically preempts processes executing in user mode so that the processes cannot monopolize use of the CPU. Then asleep and wake up. A process executing in kernel mode has great autonomy in deciding what is going to do in the reaction to system event. Processes can communicate with each other. Processes can communicate with each other and suggest various alternatives, but they make the final decision by themselves. So there is a set of rules that processes obey when confronted with various circumstances or different parameters, but each process ultimately follow these rules under its own initiative. And for instance, when a process must temporarily suspend its execution, that is go to the sleep. It does so of its own free will. Consequently, an handler cannot go to the sleep because it could, if it could, the interrupted process would be put to the sleep by default. Processes go to the sleep because they are awaiting the occurrence of some event, such as waiting for input output completion from the peripheral device, waiting for a process to exit, waiting for system resources to become available, and so on. Processes are said to sleep on an event, meaning that they are in the sleep state until event occurs, at which time they wake up and enter the state ready to run. So many processes can simultaneously sleep on an event. When an event occurs, all processes sleeping on the event wake up because the event condition is no longer true. When a process wake up, it follows the state transition from the sleep state to the ready to run state, where it is eligible for later scheduling. It does not execute immediately. Sleeping processes do not consume CPU resources. The kernel does not constantly check to see that the process is still sleeping, but waits for the event to occur and awakens the process. Then, see, this is a figure for a sleep and wake up. So, this x-axis contains uh, three processes: process A, process B, and process C, whereas the y-axis contains the time. When the process A is entered, then buffer is locked. So process A go to the sleep. At some time, process B is entered. Buffer is at that time also buffer is locked. Process B go to the sleep. When process C is entered after some time, at that time also buffer locked. Process C go to the sleep. So when the buffer is unlocked, wake up all sleeping processes. All are ready to run. Process A, process B, process C, all are ready to run. But the peripherals are allocated to the process B. Process B has started its execution whenever the peripherals allocated or different input output peripherals, so buffer go to lock. So at that time process A and process C go to the sleep mode, and process B also after some time go to the sleep for arbitrary reason, and wake up after some time wake ups for unlock buffer, wake up all sleeping processes process A, process B, and process C. So context a switch eventually. So execution starts by process A. At that time, process B and process C are in sleep mode, and so on. This is the example of a sleep and a wake up state of three different processes: process A, process B, and process C. So this figure shows a different scenarios where three processes A, B, C extend for locked buffer contained for lock buffer. The sleep condition is that the buffer is locked. The process executes one at a time for find the buffer locked and sleep on the event that buffer becomes unlocked. Eventually, the buffer is unlocked, all processes wake up and enter state to ready to run. The kernel eventually selects one process, say B, to execute. So process B executes while loop finds the buffer is unlocked, sets the buffer lock and proceeds. If process B later goes to sleep again before unlocking the buffer, that is waiting for completion of input output operations, so kernel can schedule another processes to run. If it selects process A, the process A executes while loop, find that buffer is locked and goes to the sleep again. So process C may do the same thing. So eventually process B awakens and unlocks the buffer, allowing either process A or C to gain access the buffer. Thus, while sleep loop ensures that at most one process can gain access to a resource, a process and enters the sleep state instantaneously and stays there until it wake up. After it goes to the sleep, the kernel schedules another process to run and switches the context to it. So this is the completion of our first chapter, the introduction. We will take a review of this chapter. This chapter has described the architecture of kernel and its two major components are file subsystem and process subsystem. The file subsystem controls the storage and retrieval of data in user files. Files are organized into file system which are treated as logical device, physical device such as a disk, and can contain several logical devices. So each file system has a superblock that describes the structure and contains the file system, and each file in a file system is described by inode that gives the attribute of the file. The system calls that manipulates the file do so via inodes. Then content beyond the syllabus. The difference between Unix and Linux operating system. So in the development point, Linux is open source and it is developed by Linux community of developers. whereas the Unix was developed by at and T Bell Laboratories and is not open source. Linux is open source whereas Unix is not open source. In case of cost, Linux is free to use and whereas Unix is licensed operating system. Then in case of supported file systems such as ext2, ext3, ext4, JSF, register-fs, XFS, then BTRFS, FAT, FAT32, NTFS. Whereas in Unix operating system, supported file system is FS, GPFS, HFS, HFS plus UFS, XFS, and ZFS. In case of graphical user interface, Linux uses KDE and GNOME. Other GUI supported are LXDE, XFCE, Unity, Mate. In case of Unix, Unix was initially a command-based operating system. Most of the Unix distributed now have GNOME. In point of uses, Linux is used in wide varieties from desktop, servers, smartphones to main, mainframes. In case of Unix, Unix is mostly used on servers, workstations or PCs. From the point of default shell, there are bash shell that is born shell, born again shell that is bash is a default shell for Linux, whereas born shell is also a default shell for Unix. In Linux, bash shell, whereas in Unix, born shell. Then, in case of target processor, Linux was initially developed for Intel's 86 hardware processors. Now it supports a 20 plus processor families. Whereas in Unix, CUnix supports PA, PA, PA RISC and Itnum family. In case of example, Linux is Ubuntu, Debian, GNU, Arch Linux, etc. In case of Unix, examples Sun operating system, Solaris, SCO Unix, AIX, HPUX, Ultrix, etc. This is the difference between Unix and a Linux operating system. And then we move towards the MCQ of this chapter. So first MCQ, which of the following have lower priority according to the process execution level? There are four options: clock, machine errors, software interrupts, disk. What will the answer? Which of the following have lower priority according to process execution levels? Low priority for process execution level, clock, machine errors, software interrupts, a disk. Can anybody? So answer is a software interrupts. As per process execution level, low priority for a software interrupts. Then second question, which of the following have higher priority according to process execution level? Clock, machine errors, software interrupts, disk. The highest priority as per a process execution level to clock. Then question third, Unix system is written in middle level language, high level language, both A and B, and none of the above. Unix system is written in both middle level language and high level language. Then question fourth, Unix system hides the dot dot from the user. Machine architecture, system architecture, software architecture, and none of the above. Unix system hides dot dot from the user. Machine architecture, system architecture, software architecture, none of the above. So answer is a system architecture. Then fifth question, buffer cache is kept in between. Buffer cache is kept in between A, file system and character device, B, file system and device drives, C, file system and hardware control, D, file system and block devices. So buffer cache is kept in between file system and block devices. Then a sixth question, system call interface is the interface between system call interface is the interface between user level and hardware level, user level and kernel level, kernel level and hardware level, or none of the above. System call interface. It is system call interface is the interface between user level and kernel level. Then which of the following is not a type of a file? Which of the following is not a type of file? A regular, B a special, C a device, D inode. So inode is not a type of a file. Then which type of user programs are not provided by system call interface through libraries? Which type of user programs are not provided by system call interface through libraries? A. Assembly programs. B. C programs. C. C++ programs. D. All programs. So assembly programs are not provided by system call interface through libraries. Hardware control is placed in user level, kernel level, hardware level, or none. Hardware control is placed in user level, kernel level, hardware level, or none. It is placed in kernel level. Then next, bootstrap code required to boot and initialize the operating system is kept. Bootstrap code required to boot and initialize the operating system is kept. Superblock, boot block, inode list, data block. bootstrap code required to boot and initialize the operating system is kept boot block. Next question. Which of the following is not kernel data structure of the file? Which of the following is not kernel data structure of file? First, U area, that is user area, then file table, user file descriptor UFD table, inode table. So user area is not kernel data structure of a file. Next, which of the following is not kernel data structure of a process? User area, file table, UFD table, inode table. So inode table is not kernel data structure of a process. The next question, every file has inode or inodes. One, two, more than one, or none. Every file has inode or inodes. One, two, more than one, or none. So every file has one inode. Every file has one inode. Then every file has a link or links. Every file has link or links. One, two, more than one, or none. Every file has more than one link or links. Every file has more than one link or links. Next question. Inode contains dot file owner, access permission, access time, or all of the above. So inode contains all of the above, that is file owner, access permission, access time. Then next question, internal representation of file is given by internal representation of file is given by file name, path name, and inode or a link. Internal representation of file is given by an inode. Internal representation of file is given by an inode. Then next question, process 0 is called as pager, swapper, init, or none of the above. A pager, B swapper, C init, D none of the above. Process 0 is called as swapper. Process 0 is called as a swapper. Then next question, U area contains, that is user area contains A control information, B status information of process, C both A and B, and D none of the above. So user area contains both control information and status information of the process. And these are the assignment questions. What are hardware assumptions needed to run Unix operating system? Explain architecture of Unix operating system with the help of block diagram. Explain the architecture of kernel. Explain the following terms of hardware assumptions for the Unix operating system. A kernel model, B user mode, C interrupts, D exceptions, and E execution level. All students, have you any doubt of this chapter? Any part, any concept? All students go to the Google and type joinmyquiz.com. All students go to the Google and type joinmyquiz.com. Hello, all students go to the Google. All students go to the Google and type joinmyquiz.com. I will take a test through Google. All of you audible my voice? My voice is audible. Give any comment in chat box. Okay, all, all of you listening. So go to the Google and type joinmyquiz.com. See on screen joinmyquiz.com. Still, no one has joined to join my quiz.com. Still, no one has joined. Go to
सर
the
जॉईन झालोत आम्ही. स्टार्ट करा.
सर आम्ही जॉईन झालोय.
5
स्टुडंट्स जॉईन झालेत.
here. I am seeing zero students.
56 जण जॉईन झालेत सर.
Zero दाखवतात की.
तुम्ही एकदा स्टार्ट तरी करा.
Quizzes.com ला बघा सर.
No player is currently. No player currently in game. स्क्रीन वरती कोड दिसतोय तोच कोड टाकलाय का बघा बर.
हा
होय
सर
होय.
तोच टाक.
नंतर व्हॉट्सअप वरती दिलाय बघा मी कोड.
62 जण आहेत सर.
एक पण दिसत नाही की स्क्रीन वरती बघा की झिरो दाखवतोय इथं.
Quizzes.com टाका की.
जॉईन माय
तुम्ही
क्विज
दुसरीकडे
डॉट कॉम.
चालू केलं असेल सर.
नवीन टॅब मध्ये Quizzes.com ओपन करा.
1 minute. One minute. Wait for a minute. All students, wait for a minute. Those students who has not joined the quiz, please join. Remaining students, do fast. Remaining students, solve fast. We are going to start next chapter. Remaining students, solve fast. Okay, we congratulate these top 5 members. A division roll number 30, A division roll number 61, A division roll number 59, Pranesh, and B division roll number 8. Congratulate them who have secure their rank in first top 5. Okay, we move towards in next chapter, chapter 2. That is a buffer cache. The syllabus of this chapter is buffer header, structure of the buffer pools, scenarios for a trial of buffer, reading and writing disk blocks, and last point, advantages and disadvantages of buffer cache. So in introduction, the kernel maintains files on mass storage devices. The kernel maintains files on mass storage devices such as a disk, and it allows processes to store new information or to recall previously stored information. When a process wants to access data from a file, the kernel brings data into main memory where the process can examine it, alter it, and request that the data be saved in the file system again. For example, the kernel reads a data from the first file into memory and then writes the data into second file. Just as it must bring file data into memory, the kernel must also bring auxiliary data into memory to manipulate it. For instance, the super block of a file describes the free space available on the file system. Among the other things, the kernel reads the super block into memory to access its data and writes it back to the file system when it wants to save its data. Similarly, the inode describes the layout of the file. The kernel reads the inode into memory when it wants to access data in a file and writes the inode back to the file system when it wants to update the file layout. It manipulates these auxiliary data without explicit knowledge or request of running processes. The kernel could read and write directly to and from the disk for all file system process or all for all file system access, but system response time and output, that is throughput, would be poor because of the slow disk rate transfer. So kernel therefore attempts to minimize the frequency of disk access by keeping a pool of internal data buffers called the buffer cache, which contains the data in recently used disk blocks. Then introduction of buffer header. During the system initialization, the kernel allocates space for a number of buffers configurable according to memory size and system performance constraints. A buffer consists of two parts: a memory array that contains data from the disk and a buffer header that identifies the buffer. Because there is a one-to-one mapping of buffer header and data arrays, buffer header to data arrays, the ensuing text will frequently refer both parts as buffer, and the context should make clear which part is being discussed. The data in the buffer corresponds data in logical disk block on a file system, and the kernel identifies the buffer contents by examining the identifier fields in the buffer header. So the buffer header in memory copy of the disk block. The contents of disk block map into the buffer, but the mapping is a temporary until the kernel decides to map another disk block into the buffer. A disk block can never map into more than one buffer at a time. If two buffers were contain data for one disk block, the kernel would not know which buffer contained to the current data, could write incorrect data back to the disk. For example, suppose a disk block maps into two buffers, buffer A and buffer B. If the kernel writes data into buffer A, then into buffer B, the disk block should contain the contents of buffer B if all write operations completely fill the buffer. However, the kernel reverses the order when it copies the buffers to the disk. The buffer block will contain incorrect data. This is the introductory part of buffer and buffer header. Then remaining part will be will be in will be take in next lecture. We stop here. If you have any doubt in chapter first, then please ask. Otherwise, write your roll number in chat box and leave the session.